So let's consider one more thing here about waves. So we got a wave, and I want to find we already know the equation of a harmonic wave, but there are other kinds of waves. There are like solitary waves that move as just a wave pulse. There's other non-harmonic waves that move. So there is, in fact, though, an equation that we call the wave equation, that any function that fits that wave equation is in fact a wave. And so what we want to do is actually see what that wave equation looks like. So what we're going to do is we imagine a wave here, and let's look at a little piece of the wave right here. Okay, so if we assume that the wave does not have a huge amplitude, so let's assume it's a small amplitude right here. So you have a little piece right here. So that means there's a force pulling here and a force pulling there. Now, one of the big problems here with trying to explain this is why do these forces not equal and opposite? Well, because technically they are slightly different angles right here. And so one, even though the magnitude, the force is the same, because the angles are slightly different, that means this little piece of material right here gets either more up force or down force, and so it moves either up or down a little bit, depending on which way the wave is moving. And so that little balance right there is kind of the thing. So what we can do is we can say, okay, this end of it is some position x, and the other end is at x plus delta x. So we'll say the difference here is some little delta x right here. And so the total y force is going to be F sine theta 2 minus F sine theta 1. Okay, now we're going to assume that mg is negligible. So we're going to assume that the tensions are so big that these forces drown out anything else. So this is obviously the total y is going to be F sine theta 2 minus sine theta 1. Okay. Now, small angle approximation. We know that sine theta is approximately theta. Well, cosine theta is 1 minus theta squared over 2 factorial plus theta 4 over 4 factorial minus theta 6 over 6 factorial. It's all the evens. Okay, so if you do the expansion, so that means for small angles, cosine theta is approximately 1. Well, tangent theta is sine divided by cosine. So for small angles, tangent theta is approximately theta. Well, that's about the same as sine theta. So that means we could approximate small angle approximation Fy equals F tan theta 2 minus tan theta 1. Okay. So we'll look at that just in a second here. Okay. And so we've got this piece of a wave right here. One end is x, the other end is x plus delta x, because that's some distance delta x right there. Okay. And so now we have the total y's. Okay. Now, the other thing, though, is that we know that is equal to MA. So MAY, okay, is equal to F tan theta 2 minus tan theta 1. Now, M is going to be mu delta x. AY is the second derivative of y with respect to time squared. Okay. Or I can just leave it as AY for right now. Okay, I'll leave it for AY for right now. Okay, so F tangent theta 2 minus tangent theta 1. Okay. So let's look at this and say, well, why don't we divide through both sides by mu delta x? So we have AY equals F over mu delta x tan theta 2 minus tan theta 1. Okay. Well, AY is the second derivative of y with respect to time. F over mu, okay, and so what we got delta x, but the tangent is the derivative, so that would be tangent, not tangent theta, but the tangent there, so that's going to be, the tangent, is the derivative, the function right there, it's the slope is the derivative, so that's going to be dy dx at x minus dy dx at x plus delta x. Okay, if we take the limit as delta x gets really small, that's going to be another derivative. So we have the second derivative of y respect to time squared equals f over mu times the second derivative of y respect to x squared. Okay, well, really, we know that y is a function of both x and time. Okay, so that means that really this should be written as the partial derivative of y, second partial respect to time squared, equals f over mu, second partial derivative of y respect to x squared. Now, we know that the speed of a wave is square root of f over mu. So speed squared equals f over mu. So what we can say is that the second derivative of y respect to time squared equals c squared, second derivative with respect to x squared. Or this is often written as the second derivative respect to x squared equals 1 over c squared, second derivative of y respect to time squared. Okay, either way of writing it is the same thing, and this is the wave equation. Any function that the second derivative respect to x is proportionate to the second derivative respect to time turns out to be a wave. And so what we discover in physics 2 is for electromagnetism that an electric field that is different in different positions, if the second derivative of the electric field with respect to position is proportionate to the second derivative with respect to time. In other words, it's a changing electric field. It changes in both space and time. And if the two second derivatives are proportionate to each other, then that means it propagates at a certain speed. And so, that's how we discovered that actually light is electromagnetic radiation. This wave equation turns out to be very interesting also because it turns out that Erwin Schrödinger, working with the electrons in an atom, discovered that the second derivative with respect to position is proportionate to the second derivative with respect to time. That means that you can actually, in fact, that we call this the Schrödinger equation, and that Schrödinger equation actually defines the wave properties of electrons around an atom. And so it turns out that you can describe that you got the nucleus of atom, you got electrons out here, and they act like they are in standing waves, and only certain standing waves fit in an area, which means only certain standing waves fit around here, which means only certain energies are possible. So that means that you only have certain quantized energy states and no energies in between, because you're going to get no standing waves in between. And so that led to the development of the basic quantum mechanics or quantum theory. And and it came from the fact that you can describe the electrons around the atom with something that turns out to be a wave equation. And once you realize it's a wave, you realize it has to be standing waves, and then all of a sudden you get quantum physics, you get the electron structures, you can solve that to figure out the particular energy states that an atom can have, and now all that is coming from a wave equation. So that's why wave equation, which looks pretty, straightforward. Second derivative of y respect to position squared equals 1 over c squared. Second derivative of y respect to time squared. That equation right there becomes very, very fundamental. Okay, now good news and bad news. Good news, this is very fundamental. We just covered it and we just explained it. So that's good news. More good news or bad news, depending on how you look at it, is we're not going to actually use it this semester. I just want you to know it. Know that this exists. But we're not going to actually make you do the second derivatives or anything. But if you had a function and you plugged in that function and compared the two second derivatives, then the coefficient of proportionality between the two would be 1 over the speed squared. So this is one way of finding the speed of a wave if you had a function for a wave. And again, it's another way of checking to see if you actually have a wave function. Because if the two second derivatives are not proportional to each other, it's definitely not a wave.